7 functions of capacitor in modern electronics. What is a capacitor? A capacitor is an electronic component that stores and releases electrical energy. It's made of 2 metal plates separated by an insulator, dielectric. When connected to a power source, one plate fills with positive charge, the other with negative charge. The energy is stored in the electric field between the plates. Everyday analogy: think of it like a rechargeable bucket for electricity. It fills up quickly when power is available. It empties just as quickly when the circuit needs energy. Unlike a battery, which stores energy chemically and releases it slowly, a capacitor stores energy electrically and can release it in a split second. Key features of a capacitor: fast charging and discharging, great for short bursts of energy. No chemical reactions, longer lifespan than batteries in many uses. Versatility, used for filtering, timing, tuning, energy storage, motor starting, and protection. A capacitor is a tiny energy tank and filter that helps electronics run smoothly, storing, smoothing, tuning, protecting, and timing signals. Number 1 is energy storage in a capacitor. No formula version. A capacitor is like a tiny electrical bucket. Instead of holding water, it holds electric energy. Inside, it has 2 plates with an insulator, dielectric, between them. When you connect it to a power source, one plate fills up with positive charge and the other with negative charge. These opposite charges stay separated, creating a kind of tension or electric field between the plates. That tension is the stored energy. Brain, everyday comparisons. Water tank analogy. Imagine filling a tank with water. Once it's full, you can release the water in one quick burst. A capacitor does the same with electricity. Battery's faster cousin. A battery stores energy chemically and releases it slowly. A capacitor stores energy electrically and releases it almost instantly. Pushpin real-life uses of capacitor energy storage. Camera flash charges up, then dumps all energy in one bright burst. Emergency backup keeps memory chips alive for a few seconds if power fails. Bridging gaps fills in tiny power interruptions so devices don't restart. Backhand index pointing right, in short. A capacitor soaks up energy quickly and can release it just as fast whenever the circuit needs a quick push of power. Number 2 is power supply smoothing, filtering. The problem: unsteady power. Most electronics don't like bumpy power. When AC from a wall is converted to DC, what devices need, the output isn't perfectly smooth. Instead of a steady line of power, you get a ripple. Think of it as waves instead of calm water. Battery, the capacitor's role. The peacemaker. A capacitor steps in like a shock absorber. It charges up when the voltage rises. It releases energy when the voltage dips. The result? The ups and downs get ironed out, leaving a much smoother, more stable DC supply. Brain, everyday analogy. Imagine you're riding a bike on a bumpy road. Without suspension, you feel every jolt. A capacitor acts like the suspension system. It cushions those bumps, giving you a smooth ride. In electronics, that smooth ride means your phone, laptop, or TV gets clean power. Pushpin real-life uses. Laptop chargers deliver steady DC power, so your computer doesn't crash. Audio systems prevent hum or noise from unstable current. Microprocessors need ultra-clean power. Even small ripples can cause errors or resets. Backhand index pointing right, in short. Capacitors and power supply smoothing are like noise-canceling headphones for electricity. They filter out the rough edges, so your device hears only the clean, steady beat of power. Number 3 is coupling and decoupling, signal separation and noise reduction. Coupling, signal separation. Imagine you want to pass music, an AC signal, from your phone into a speaker amplifier. The music signal rides on top of some unwanted DC level, like static voltage that can harm the next circuit. A capacitor steps in like a gatekeeper. It blocks DC, the junk you don't want. It passes AC, the music, the actual signal. Backhand index pointing right result. Your amplifier gets only the clean sound, not the static baggage. Analogy. Think of coupling as a sieve. It lets the useful water signal through while holding back the sand, DC. Muted speaker, decoupling, noise reduction. Now flip the situation. Imagine a microchip in your laptop. It wants steady, clean power. But power lines are noisy, full of little spikes and fluctuations caused by other parts of the circuit switching on and off. A capacitor sits close to the chip and acts like a shock absorber. It absorbs sudden spikes of noise. It fills in tiny dips in voltage. Backhand index pointing right result. The microchip runs smoothly without crashing or glitching. Analogy: decoupling is like putting a cushion under a vibrating machine. The cushion absorbs the shakes, keeping everything stable. Pushpin real-life examples. Coupling audio devices, radios, and TVs, passing only the signal you want. Decoupling computers, phones, and any digital system, keeping the power clean. Backhand index pointing right, in short. Coupling equals separating the signal from unwanted baggage. Decoupling equals calming down noisy power, so circuits stay stable. Number 4 is tuning and frequency selection. The challenge: so many signals at once. Right now, the air around you is packed with radio, Wi-Fi, TV, and phone signals, all at the same time. But your radio or phone can't process them all together. It needs to pick one frequency and ignore the rest. Level slider, the capacitor's role. The selector. Capacitors, when paired with coils and inductors, create a sort of frequency filter. By adjusting the capacitor's value, the circuit can tune in to just one frequency and block the others. This is how your radio finds 101.5 FM without blasting you with all the other stations. Brain everyday analogy. Think of a music concert with lots of instruments playing. You only want to hear the violin. A capacitor, with its partner the inductor, acts like a musical ear that singles out the violin sound while tuning out the rest. Or picture an old radio knob. When you turn it, you're changing the capacitor's value. That's like twisting a lens until the picture comes into focus. Only here, it's sound waves coming into focus. Pushpin real-life uses. Radios pick out one station from dozens. Televisions select the right channel frequency. Wi-Fi and phones tune to the exact frequency band they need for fast communication. Backhand index pointing right, in short. Capacitors help circuits tune into the signal you want and tune out the noise you don't, like a DJ choosing the next track while silencing all the others. Number 5 is timing and oscillation timing, delays and intervals. A capacitor can charge up and discharge at a predictable pace. The bigger the capacitor, the longer it takes to charge or discharge. Circuits use this behavior to create delays or specific time intervals. Examples: automatic light that stays on for 10 seconds after you press a button. A washing machine cycle timer. The blinking of indicator lights in cars. Analogy: think of filling a bucket through a small hole. The bucket takes time to fill. That filling time is a delay a capacitor gives in an electronic circuit. Counterclockwise arrows button oscillation, repetition, and waves. If you connect a capacitor with the right partners like resistors or inductors, it doesn't just delay, it starts creating repeating patterns. This can generate pulses, beeps, or continuous waves. In fact, many clocks, alarms, and radios rely on this oscillating behavior. Examples: quartz watches, steady clock signals. Microprocessor clock signals, the heartbeat of computers. Sound effects in musical keyboards or synthesizers. Analogy: picture a swing in a playground. Push it once, charge it. It swings back and forth, oscillates. With the right timing, you can keep it swinging steadily. That's exactly what capacitors help do with electrical signals. Pushpin in short. Timing equals controlling when something happens. Oscillation equals creating a steady rhythm or repeating signal. Number 6 is motor starters and power factor correction motor starters, helping motors get moving. Electric motors, like in fans, pumps, or fridges, don't start spinning easily on their own. They need an extra push. A capacitor gives that push by creating a phase shift. In plain words, it makes the motor's magnetic field twist strongly enough to kickstart the rotation. Once the motor is running, some designs keep the capacitor connected for efficiency, while others disconnect it after the start. Analogy: think of trying to push a heavy swing. If you push straight on, it barely moves. But if you push with the right angle and rhythm, it swings smoothly. The capacitor is that angled push that gets motors going. Examples: ceiling fans, refrigerators and air conditioners, water pumps, high voltage power factor correction, making power use efficient. In factories and even homes, some machines waste electricity by drawing more power than they actually use. Kind of like drinking through a straw, but spilling half the juice. Capacitors fix this by balancing the current and voltage so machines run more efficiently. This reduces wasted energy, lowers electricity bills, and prevents overloading of power systems. Analogy: imagine you're carrying a heavy box but leaning backward. You're wasting effort just to stay balanced. A friend comes along and steadies the box from the other side. Now, all your strength goes into moving forward, not fighting imbalance. The capacitor is that helpful friend. Examples: industrial plants with lots of motors, large office buildings with heavy HVAC systems. Even power grids use capacitors for stability. Pushpin in short. Motor starters. Capacitors help motors overcome inertia and start spinning. Power factor correction. Capacitors help systems use electricity more efficiently, reducing waste and costs. And number 7 is protection, transient suppression, the problem: voltage spikes. Electronics don't like surprises. But in the real world, circuits face sudden jolts of extra voltage, called transients or spikes. These can come from lightning strikes, switching large appliances like an AC or fridge, or even static electricity. If left unchecked, they can burn out chips, crash systems, or shorten a device's life. Battery, the capacitor's role: the shock absorber. A capacitor acts like a sponge for electricity. When a sudden spike arrives, the capacitor quickly soaks up the extra energy, preventing it from reaching sensitive parts. Then it gently releases the energy back when the circuit is stable. Brain, everyday analogy. Imagine a water pipe. A sudden surge in pressure could burst the pipe, but if you have a side tank, the capacitor, the extra pressure flows into it instead, protecting the pipe. In electronics, the pipe is your circuit, and the capacitor is the side tank, saving it from blowing out. Pushpin real-life uses. Surge protectors keep your laptop or TV safe during power spikes. Automotive systems protect onboard electronics when you start the engine. Switching circuit snubbers stop sparks or arcs when turning devices on-off. White heavy check mark in short. Capacitors and protection are like airbags in a car. You hope you never need them, but when a sudden jolt hits, they absorb the shock and save the rest of the system.